attention. Dr. We have two more participants, which is not mute. Okay, never mind. Okay. Okay, bismillahirrahmanirrahim. Alhamdulillah rabbil alamin wassalatu wassalamu ala asyrafil anbiya wal mursalin wa ala alihi washabihi ajmain. Assalamualaikum warahmatullahi wabarakatuh and a very good morning to all of you. My name is Dr. Zubaida from Multimedia University and I'm also the Assistant Secretary of the IEEE EDS Society Malaysia section. I will be your MC today. I will be assisted by Dr. Haslina Jaafar from University Putra Malaysia as the technical moderator. Okay, on behalf of IEEE Electronic Devices Society Malaysia chapter, I would like to extend a very warm welcome to all of you for today's event, the very first virtual IEEE EDS Malaysia Distinguished Lecture 2020. For our session today, you can send any questions by writing in on the chat box. I will select the relevant questions to be asked to speakers at the end of each session talk. Please be informed that all the participants in this lecture will be given e-certificates. All you have to do is to fill up the feedback form. They'll be given the link at the chat box at the end of this lecture session. We will email you the e-certificate. To begin with our program today, we are pleased to invite our past chair, Associate Professor Dr. P. Susita Menon from Universiti Kebangsaan Malaysia, who is also the IEEE EDS Region 10 representative to deliver the welcoming address speech. Please.
Okay. Thank you so much, Dr. Zubaida. Can you hear me? Can you hear me?
Yes, we can hear you, Dr. Susi.
Okay, right. So thank you, Zubaida, and also welcome to Prof. Xing from NTU Singapore. Thank you for accepting our invitation for a DL talk. And on behalf of EDS President, Prof. Mia Mayapan from NESA, and also Vice President of Region and Chapters, Murthy Polawarapu, I would like to congratulate EDS Malaysia for successfully organizing the first virtual distinguished lecture for EDS Malaysia. And I would like to give regards from EDS Subcommittee for Region and Chapters Chair, Prof. Albert Chin from National Chiao Tung University, Taiwan. On behalf of him and also myself as the Vice Chair, congratulations to EDS Malaysia. And I would like to congratulate Prof. Nohayati Soin, the Chair of EDS Malaysia. So just as a background for the participants, EDS Malaysia has won the Outstanding Chapter Award in Region 10 in 2014 and 2018 for the outstanding activities that they have done. And I hope with the new set of volunteers in EDS Malaysia, EDS Malaysia will prosper and further achieve many greater heights in EDS committee. So thank you very much. And I hope we'll have a very successful DL lecture, which is done virtually. Thank you.
Thank you, Dr. Susi, for a warm welcoming speech. Next, we are honored to have our first lecture by Professor Zhou from School of Electrical and Electronic Engineering, Nanyang Technological University, Singapore, to share with us on a topic titled Monolithic Co-integrations of 3-5 materials to Foundry's silicon CMOS in a single chip for novel integrated circuits. First, let us get to know about him. Professor Zhou obtained his Bachelor of Engineering degree in Electrical Engineering from Singapore University in 1983, Masters of Science and PhD degrees in Electrical Engineering from the University of Rochester in 1987 and 1990 respectively. He has been with the School of Electrical and Electronic Engineering, Nanyang Technology University, Singapore since 1992. His past research interests include Monte Carlo simulations of photocarrier transport and ultra-fast phenomena, as well as mixed-mode circuit simulations and CAD tool development. His recent research mainly focuses on nanoscale CMOS compact model development. His research group has been developing a unified core model for nanoscale bulk, SOI, double gate, nano-wise CMOS, as well as 3.5 HEMTs. Without further ado, I would like to invite Professor Xing Zhou to give his speech, his talk. Professor Zhou, you are given about 40 to 45 minutes for your talk.
Thank you. First of all, let me thank you for the EDS Malaysia chapter for organizing this virtual DL. I've been given many DL talks, but this is my first time for this virtual one. Let me first share my screen. Can you all see?
Not yet, Prof. Yes.
Okay, let me choose a full screen. Okay. How to remove this? Okay. Well, the title of my talk is Monolithic Co-integration of 3.5 materials into Foundry CMOS, silicon CMOS in a single chip for novel integrated circuits. Let me see how to remove this, because this small window is blocking my view. Oh, anyway. Well, I'll first give a brief introduction to this Smart Lease program, which stands for Singapore MIT Alliance for Research and Technology. Low energy electronic systems. This has been a 10-year multi-million-dollar program. I'm involved in this. This talk is based on the work program. So I'll first give a brief review of the history on the monolithic integrated circuits, and that leads to the motivation of this new heterogeneous integrated system. Then I'll briefly cover this the technology for this program, which is a double layer bond and transfer process. Then my group in this program has been mainly in the modeling and the PDK development. So I'll go through this idea of the hybrid 3.5 plus CMOS PDK for monolithic 3.5 silicon circuit design. For the second part of my talk, I'll go through this some examples. The compact model my group has been developing is started with the bulk CMOS, SOI double, and now we are extending this to 3.5 devices. For this talk, I won't go into model details, all those equations, but I'll show some examples of the results from this program. So including Cascode, Gananath, and LED with CMOS driver and scalable RF compact modeling and the trap charge model. Then I'll end with a summary on this program. So as we know, the invention of the integrated circuits, one is the Kilby's patent, which is based on the wire bond interconnect. And another one is the Noyce patent, which is the monolithic interconnect. And today's technology is actually all based on this monolithic implementation. It's hard to imagine how can we achieve such a high degree of integration with wire bonding. So as we already seen this mainstream silicon CMOS has been driven by this so-called Moore's law. but in the recent decades, it's been slowing down. So any novel IC for economic growth based on this traditional mature path is slowing down. And we've been also hearing about the so-called compound semiconductor, the gallium arsenide, that has been the material of the future for several decades. Now we're entering a new era. So now if you look at any systems, for example, iPhone, if you open the iPhone, you know, the main part of the system is digital CMOS, based on silicon. However, those I/O power, those are all separate modules based on 3.5. So now about around 10 years ago, there are two technologies with the emerging GaN technology. One is the so-called CMOS compatible GaN on 8-inch wafer. Another one is the 3.5 silicon co-integration, which is this SMART program. There's some fundamental difference between the two. The compatible CMOS compatible GaN is basically we're processing a GaN device on a silicon wafer with CMOS compatible technology, but this co-integration is actually putting two different material and devices onto the single die. Well, the next 2 decades will produce a radical shift in information systems. So new integrated circuits that are fundamentally different will be the key. So, but the current, you know, the infrastructure has been the CMOS. We don't want to start new and throw away all those existing infrastructure. So the idea is how we can insert this 3.5 material into an existing CMOS infrastructure. If we can do that, and you know, the 3.5 device and the power batteries can all be achieved with the current infrastructure. So this requires a material to circuit vertical knowledge, you know, the exploring new functionalities in the silicon-based IC. So here's a top view of the this idea of the vertical integration. So we work with a existing silicon foundry. That is the front-end CMOS has been implemented in the traditional, say, 8-inch wafer from a foundry. Then we seal the wafer, take the wafer to our lab to integrate this 3.5 layer. Then we process the 3.5 device together with the CMOS. After that, we seal the wafer and send back to the foundry for backend. To the foundry, this as if the wafer has never gone out of the foundry. So this will leverage the existing infrastructure. So if we can do that, all those other studies like thermal management, reliability, all these can be done, can be studied. So this is the core of the LEAS technology. So there's a website here. You can learn more information. Well, let me go through this so-called double layer bond and transfer process. So we start with an engineered substrate containing both CMOS and, well, we started with this CMOS wafer. For example, the front-end silicon MOSFET already been fabricated in the foundry with the top layer sealed. Then we take this wafer in our lab and put a handle wafer on the top. Next step, we remove the bottom substrate. Then we bond second layer with the 3,5 materials. Then after that, we remove the handle wafer. So this is the sequence of the double layer bond and transfer process. If we can do this for double layer, imagine that we can do the same process for triple or multiple layers of different 3,5 materials. Here's a brief overview of the hybrid device fabrication. So this is the CMOS device already embedded in the silicon layer with the dielectric on top, and then the 3,5 wafer already bonded at the bottom of the wafer. Then we dig the window where the 3,5 devices will be fabricated on the same wafer. Then we fabricate the 3,5 device. Then we seal the wafer, refill the wafer with a planarization of the wafer surface. Then we do the tungsten plug to reach the 3,5 layers. Then redeposition of planarization. Then we do the interconnect between silicon and 3,5 devices. This can be side by side in the layout. So this vertical innovation, including materials process and circuit design vertically. So this applies to different materials, different applications. So we have a few examples like a HAMT platform for GaN InGaAs, LEDs, silicon-based battery or solar platforms. Here's just a few examples. Well, for my group, we're developing this PDK. So basically, we get a silicon PDK from the Foundry, and then we develop PDK and models for the 3,5 device, and then we have a joint hybrid PDK that permits a direct integration of 3,5 devices into silicon CMOS in a single design platform, including the design rules with the interconnect between the two type of devices. One example is this Cascode GaN HAMT. As we know from market, we have this discrete packaged by wire bonding of GaN with silicon CMOS for the Cascode amplifier. So this is done through wire bonding. We have product of this kind. Well, with the monolithic Cascode implementation, this can be done from this technology. So basically, we can have a MOSFET and GaN side by side. In our hybrid PDK, we have symbols for both and models associated with both type of device, and we can create this composite Cascode symbol and then corresponding layout, and we can create these as a library P cell, and from which we can circuit designer can build their own monolithic Cascode GaN HAMT amplifier. So here's we're augmenting CMOS Foundry PDK for monolithic integrated circuit design using CMOS and the 3,5 devices. So here's from Cadence example for the schematic and the layout and the die image. Well, we have some simulation comparison for the advantage of this approach. As we can see, the monolithic cascode Gananath, which is shown by this triangle, has this comparable high voltage up to 20 volts here, as the this D mode, similar to the D mode Gananath cascode, but it also has the advantage, compared to Si-CMOS cascode, which if you use a Gananath, it will be a negative threshold voltage, but this composite one has a similar positive threshold voltage. This is through our design and the TCAD simulation. Another example is on-chip optical link with photo generation and LED type of device with a Si-CMOS driver. So we have also implemented corresponding models and PDK for this kind of type of application. So one example is the monolithic hybrid 3-nitride LED. And this is our first demonstration of a working LED on this 8-inch CMOS wafer. So we have the corresponding PDK for CMOS and the LED with the composite symbol and the corresponding layout and the die. So we have a working device which shine blue laser light, LED lights from directly out of the 8-inch wafer. Well, second part of the talk, I'll go through some of the model work in my group within this program. So our starting, actually this work is leveraged from my group's prior work on the model development for the silicon, bulk and the double gate. And when we extend to HEMT35 device, I just list out some specific features relevant to 35 device. The first one is the 2DEG, triangular or rectangular type of quantum well. Our model included multiple subbands, not just the lowest or 2 subbands. So we developed a model including multiple subbands, and this you can see the sheet of 2DEG is similar to the charge sheet model in the conventional silicon model. So we are based on the drift diffusion of velocity saturation model, but we're including these quantum effects from the 2DEG. We have also included a moderate inversion where the Fermi level is above the bottom of the subband, but below the bottom of the subband, but still positive. So this is the so-called moderate inversion region. And for subthreshold, actually, where this structure is similar to a unintentionally doped thick body SOI. So we are leveraging on the SOI type of model for including these effects. Then for HEMT, the access region is different from CMOS LDD structure. So we use the same HEMT model as an ungated HEMT for the source and drain access region. For GaN, there's a special effect called the trap charge effect, the current collapse. So and also these are duty cycle dependent, including self-gating effects. We included all these effects, and also polarization charge and the parallel channel. There are also quasi-ballistic transport effect which is different from the classical drift velocity saturation. And another is the geometry biased scalable RF model. So that's this topic also relevant to CMOS RF modeling. Well, I won't go into model equation details, but I just show our model results in comparison with TCAD and measurement to show all these relevant effects. All the subsequent plots lines are based on our model, and the symbols are based on either TCAD or measurement. So these two plots shows the IV, IDVG characteristics. For left figure is for different drain bias, and the right figure is for different gate lengths from long to very short channel. We can see the subthreshold slope change, which is modeled by the thick undoped SOI based on the quasi 2D electrostatics. Well, the corresponding CV curve, CGG versus VG, and the drain current on the left. This is showing the doping dependence, where the substrate doping, unintentional doping changing from very low to higher value. So we see the shift in the threshold voltage is all included in the model. Well, this one shows the geometry dependence of the access region for different ratio of the gate to drain and to gate to source lengths. So our model scale physically with these geometries. Here we show the IV for IDVG and IDVD. Comparison with TCAD. And the same plots for comparison with measurement for different IDVG, different drain bias, and IDVD for different VG. This one includes the self-heating effects. This is also comparing with measurement for different drain to gate dimension. IDVG on left and IDVD on the right. This is the corresponding derivative showing the GM and the GD. The model all scales physically without refitting. For scalable geometry bias doping dependence, the traditional way of model is actually based on the subcircuit approach, where you have the intrinsic model already developed, and then you add RC elements to model the substrate and the parasitics. Then the people are trying to extract these RC values to match the measured S parameter. So this approach has been practiced all the time, including the current way people are doing RF modeling. However, imagine the way to extract these RC values, just a number for the R and the C, it won't be scalable over DC bias point, Q point. So for different DC bias, you need to extract different values. So in that sense, it's non-scalable. And also for different geometries, different doping. So all these RC values need to be re-extracted. And what if the intrinsic model is not physically scaling? Then when you go to RF with this parasitic effect, basically you're based on the somehow incorrect core model, and then plus some incorrect extracted RC value to match to obtain the so-called correct result of the measurement. So, we have been developing a physically scalable core model and subcircuit approach. Here we just show some preliminary results from our model. Basically, our model is based on the surface potential based, and this is extended to MOSFET, including a 2D EG model, and it's scalable in geometry, gate source drain, length, and substrate doping. So the model will be scalable over geometry and bias for these the subcircuit element. In other words, we don't need to extract the RC values for different viewpoints and different geometries. And model playback without refitting to for RC element values. So here we show S parameters for the S22 and S11. As we can see, the model can scale in DC, which is calibrated to the DC model, and then for high frequency. This can be very tough if we do this with conventional RC fitting. Here we show S parameter. The lines are by model, and here is all comparing with TCAD. On the left is at one gate bias, and the right is another gate bias for different lengths. This one shows geometry scaling. Here is the current gain extracted from both TCAD and the model based on the definition of the through the small signal analysis, and extract the current gain based on the unitic current gain. So here model scales for different lengths, gate lengths, from long to very short channel lengths for given bias. Here is showing model calibration to DC for IDVD and IDVG with and without self-heating. This is an example for one gate length and one particular geometry for source and drain access length. Well, we actually calibrate this model for certain corner conditions, and the scaling of this DC model, as shown before, is all scale with without refitting. So when DC is calibrated, we can play back our scalable RF model with S parameters, as shown here for the with and without self-heating. This is again comparing with TCAD. This is the current gain, H to 1. Here's an example, similar example, again, fixed gate length, but for different source and drain access region lengths. As we can see, model can play back, and the corresponding RF model also scales, so without refitting. Very high frequency, of course, still need to do more work. Well, just a few more words about the trap modeling. As we know, for GaN device, traps are generated in the gate region and also in the source and drain region. And it's reflected in the DC characteristics. If you do DC measurement with a pulse DC, and all these curve will depend on the pulse width, pulse duration, bias point. Whenever you change these values, the DC curve will all change. So how to model these physically without fitting to each measurement data? So basically, these effects are contained in the how much traps have been generated in the device, in which region. So we model the trap generation through the rate equation here, and then this equation can be solved through the transient analysis in the Verilog A platform. So these are all built into the surface potential description. So then it's easily extended to our core model. Here is the so-called gate lag effect, where is trap are generated under the gate, and this will be showing as a threshold shift, which affect the saturation region of the device. So here we can see our model. There's some model parameters can be extracted by varying the pulse width, and then the model will automatically play back and match the TCAD data. TCAD, we can specify how much the exact parameters of these quiescent and the pulse widths. So then our model accurately capture these dependencies. Here's a example for different quiescent point for two different gate voltage. So at a fixed pulse width, it also scales. Here's the transient analysis for two different gate quiescent point, and showing the trapping and detrapping range. Here's one more example for the gate lag for different pulse widths dependence. The right hand side shows a different gate quiescent point dependence. All these again is playback with the model without refitting. For the gate and drain lag effect, which is mainly due to the traps generated in the drain access region, this will influence the R-on in the linear region. So as we model the access region using the same HAMT model as an ungated HAMT, so we can also incorporate these traps into the same way. Here is the result for different pulse IV for different drain bias, quiescent drain voltage for given gate length, and all other parameters are fixed. Here is on the right is showing the drain quiescent drain voltage difference for two different gate to drain dimension. again, the model scale accurately with the TCAD. Well, as a summary, this as we described this smart lease program is an iterative innovation process and vertical innovation model encompassing materials, processes, devices, circuits, and systems. This will create a new path to future integrated circuits. And the double layer bound and transfer process, which allowed different 3.5 material platforms co-integrated with the mainstream silicon foundry technology. This will leverage existing infrastructure while exploring new frontiers. Our hybrid PDK is augmenting the foundry PDK and enable circuit designers to design novel monolithically integrated 3.5 silicon circuits in a conventional way. And we have demonstrated novel applications called these, for example, the monolithically integrated cascode Gananath without separate chip bonding, and with the CMOS and the GaN device side by side. And our first application of this technology is actually to LEDs on 8-inch silicon wafer with CMOS driver. We also developed this scalable RF model with geometry bias scalability. Physics-based trap model also allow these reliability studies to be physically studied. Well, as a summary, to look back, this program has been in the 8th year, and this slides actually I borrowed from the program director, Professor Eugene Fitzgerald from MIT. He has been practicing this so-called iterative innovation model. So unlike the traditional thought of innovation, you start with some novel invention of some technology, and then you go through some linear implementation, and then you eventually have that technology spin off in the market. And that's something is hard to think if you can have some novel technology 10 years ahead of time and find a market 10 years later. So this iterative model actually start with 3 components. So from the technology, market, and implementation. So initially when this program was proposed, all these 3 parts has been largely not well clearly defined because there are so many uncertainties, and we leave it in that way. And over the years, we've been reducing the uncertainties in each of these 3 components. So by the time when the program evolves, we know we're focusing more on the LED, and then we will work with the Foundry on the 8-inch the demo, and this will be for particular, more specific market application. So this idea of iterative innovation will be successful eventually when it converges to to this new type of imagine if we can put 3.5 devices in the same die as silicon devices. So the applications of this new technology will be endless. Well, this is my talk. Thank you.
Thank you, Prof.
Okay.
Zhou. So we have a few questions here in the chat box. I will just read from Mr. Marwa Yusuf. Okay, number one, is gallium nitride is for memory and silicon for processing element or vice versa, or we are free to choose programmatically? And his second question is, are we free to choose RC circuit configuration using this material?
Well, GaN is 3.5 is more application-wise is more for one area is for RF, high frequency device. The other is power. But this LED is a very unique application if you can integrate into CMOS. Of course, most of the current product is all 3.5 alone. The second question is on the RC. What's the second question?
Are we free to choose RC circuit configuration using these materials? Is there any?
RC, so you mean for the subcircuit to model this device?
I'm not sure what his questions on that one.
Can you read the question again?
Are we free to choose RC circuit configurations using these materials?
I suppose he meant for, because I mentioned the subcircuit RC element, so I suppose he meant for the choice of these RC values for this 3.5 device. Well, in high frequency modeling, I think it's all based on the subcircuit. Even in the CMOS domain, so CMOS RF modeling, people are also using this approach. The main question is how we choose those RC values. So in traditional way, people are extracting those values based on the fitting to the measured S parameter. But as I mentioned, this won't be scalable if you change the DC bias point or you change the geometry. You need to extract a new RC value. It's a number. But here, we're trying to model these R and C physically by equations rather than extracted value. So then once we have the equation physically developed, we extract certain boundary parameters, then for all other DC bias and the geometry, it will scale by itself.
Okay, thank you, Prof. I think I will just read one more questions. I know Mr. Marwa write some more questions here. Maybe I hope that answer your question just now. Okay, Mr. Marwa. And then I have one more question. I think it's same about the same questions with Dr. Susie questions. What are the challenges when fabricates HEMT when there is already a CMOS device, especially plasma etching and annealing? Something with challenges, I guess, when fabricating this HEMT?
For fabrication challenges, I'm not a process guy, but I think, well, the main challenge of this new technology is how to, fabricate 3.5 together with CMOS. CMOS device front end already embedded in the hybrid wafer. So of course, you need to consider the thermal budget, all these things. Yeah, I think that's the main, the special challenges for this hybrid technology. Conventionally, for 3.5, whatever those 3.5 device fabrication, I think challenges is by 3.5 itself. But for this co-integrated one, there are additional ones.
Okay, thank you, Prof. Zhou. I think that's all the questions. I think there's a few more, but Okay, I think we already out of time for the first presentation, so I think
That's fine. Yeah.
yeah. So I think we just if you have any more questions for the participants, maybe we can direct to Professor later.
So this virtual conference, there's no interactive. It's all through this chat, right?
Yeah, we organize this way lah, so that
This is my first time, so there's still not like active interaction from the participants.
So I will just read question from the chat box. Yeah.
Good to know. Thank you. Thank you.
Yeah, for the participants, for more questions, please email to Prof. Zhou at there's email address there written in the chat box. Okay.
Okay.
Right. Okay. Thank you.
Thank you. Thank you.
Yeah. Okay. Thank you, Prof. So I hope the information sharing by Prof. can enlighten us about this topic. Okay. So now we will proceed with our program with the next speaker. The next speaker is from the Sambalpur University, India. He will be sharing with us on a talk titled Influence of Structural and Operating Parameters on the Performance Characteristics of Graphene Nanoribbon Field Effect Transistor GNRFET. The speaker is Professor Gananath. Let us get to know him. Okay, so Professor Gananath is superannuated as professor and head of the Electronics Devices Group from Sambalpur University, India, in November 2015. He obtained his PhD in 1992 in the area of microwave and millimeter wave devices. Later, he developed interest in such diverse fields as DSP for bioinformatics, medical data mining, and graphene-based electronic devices. He has more than 37 years of teaching and research experience. He has authored and co-authored more than 225 research papers in international national journals and conference proceedings. He has supervised 14 PhD and 37 Master of Field theses. He has the distinctions of guiding PhD degree in the Faculty of Both Science and Engineering. Prof. Dash has made significant contributions in the development of a simulation method of assess the effect of tunneling and diffusion current on impact avalanche transit time diode, new design approach of mixed tunneling avalanche transit time and tunneling transit time devices, formulations of a noise theory of MITAT diode using computer simulations method, and development of a noise theory analytically applicable to mixed mode operation in impact diode. Without further ado, I would like to invite Prof. Gananath to give his talk. Prof. You are given about 40 to 45 minutes for your talk. Prof.
Turn on your microphone, Professor Dash. It is off, turn off. Go bottom and microphone is.
Okay. Yeah, Prof. You can also turn on your microphone. Yeah.
Hello. Hello.
Yes, we can hear you now.
Audio is okay?
Sorry?
Audio is okay?
Yeah, we can hear you.
You can
Can you please?
Then next I go to the presentation.
Yes, please.
Sharing the content.
Yes, please.
Yeah. So my topic is influence of some structural and operating parameters on performance characteristics of graphene nanoribbon FET field effect transistors. Right. Uh, the plan of the presentation. First, I will give you some motivation. Then I will introduce graphene because it's a new kind of materials, and of course it has become old. That discovered in 2004. Graphene nanoribbon, and it is a variant of graphene. Graphene nanoribbon FET, modeling of graphene nanoribbon FET, and then some computational study, and then results and summary. Motivation is that why should we study graphene, or why should we introduce graphene into the arena of electronic devices? Because silicon electronics and scaling challenges are approaching. First, prospects of carbon-based electronics is taking over others, and graphene in this meantime emerged as a superlative, having exotic properties suitable to electronics and many other applications. See, and silicon electronics and scaling challenges. In 65, Gordon Moore noticed that the number of transistors in a square inch of IC that doubled every 18 months, and cost is half. And this goes by the name of Moore's law. And Moore's law predicts that this trend will continue for the foreseeable future. The exposure having silicon transistors has, window is blocking. Okay. The exponential trend in scaling silicon transistors has enhanced the device performance and density, satisfying the prediction of Moore's law for decades. Scaling down in each new generation has approximately doubled logic circuit density and increased performance by about 40%, while the memory capacity has increased 4 times. Yeah. Graphical depiction of how Moore's law has worked, starting from 1970, where we had only 1,000 transistors per chip, and now in 2020 we have 1 billion transistors in chip. So this is the tremendous growth in the IC technology, and straight line says that Moore's law is continuing. This is the integrated circuit scaling history. We started with 10 micrometer in 1960, and then we are now reaching 0.1 nanometer in 2040. But we are now at this point, 2020, which is having 10 nanometers. This is the transition region. Instead of this era of simple scaling, high performance material complex design, an invention of new functional devices will be coming in the future. And in this invention of new functional devices, this GNRFET comes. Now, this exponential tendency to scale silicon transistors also affects the device performance reversely due to some fundamental limitations. These limitations are the leakage current, increased power density, and device becoming small in size, reaching the atomic limit. The leakage current originates from the reverse biasing of the PN junction and weak inversion and BIPL. Increased power density and corresponding dissipated heat it in nanometer dimension also impose several fundamental physical challenges for silicon, seriously affecting the performance of the chip. More forward-looking solutions for scaling challenges of silicon electronics are the utilization of alternative channel materials such that they can be likely solved by the genesis of new materials for integrated circuits. Now, the prospects of carbon-based electronics. Germanium has been substituted by silicon roughly half a century ago by moving up on the group 4 of the periodic table. Interestingly, moving up one more block, we reach carbon, which has been widely tipped as substitute for next generation electronics due to its impressive crystal structures and several allotropes like graphene nanoribbon, carbon nanotube, and according to the International Technology Roadmap for Semiconductors, these two allotropes are prominent contenders to substitute silicon in post-CMOS technology as a potential solution by the year 2028. Now, this graphene superlative, graphene has a potential to be integrated onto silicon substrates as a new hybrid and to overcome economical and technological challenges. One-dimensional structures have remarkable electron transport properties, including high mobility and symmetric band structures. You can see this is the band structure of graphene, PK diagram, and this is that structure, hexagonal lattice. Then what are the other properties of graphene which makes it so suitable for the electronic industry? First of all, zero band gap, which may be a boom or a curse, both atomically thin planar structures. So this is a very new paradigm. That means all materials were earlier three-dimensional. Now it is a two-dimensional first material, and subsequently you have a lot of host of materials which are two-dimensional in nature. Then it is massless, then it is ambipolar. That means the same graphene can be used as P-type or N-type semiconductor. High thermal conductivity helps to dissipate the heat very quickly. High carrier concentration, the current density increases. High carrier mobility, the speed increases. For suspended graphene, we have mobility 2 into 10 to the power 5 cm square per volt per second. And for practical samples, U, however, reduces to about 10,000 to 15,000 units. Transport in such samples is ballistic, and therefore the diffusive theory that we are already following may not be applicable, so we have to devise some new ballistic transport. Remarkable current density it can support is more than 10 to the power 8 ampere per centimeter square. Now, the IC integrated circuit application of large area graphene is limited both for digital and analog ICs. For analog ICs, the saturation characteristics of graphene FET is unfavorable. That means it gives either zero or negative transconductance, which is a major hurdle in the application of graphene to analog devices. For digital ICs, the major drawback for such application of bulk graphene is its zero band gap, which makes the graphene-based FETs hard to switch off. That means the off-state leakage current is more, which leads to unprohibitively large power dissipation. Alternatives to circumvent this problem are to use the band gap engineering of graphene, which can induce a band gap under some appropriate condition, and which is in the next slide. See how we are going to engineer the band gap in graphene. There are three ways. If there are bilayer graphenes and the two layers are given an electric field, then we produce some band gap. Then if you cut the graphene into small graphene of small width, that those are called nanoribbon. That means less than 50 or 40 nanometer width. We can cut the graphene into ribbons, then we can introduce band gap. And strain engineering, that means you can pull or stretch graphene sheet, then of course it will develop some band gap also. So these are the three ways of band gap engineering. It has been illustrated here in this slide. It is bilayer, this is bilayer, so it has some gap, but this has no gap. Then graphene nanoribbon, you can see this is the picture of the nanoribbon, and this is the string. And it's pseudomagnetic fluid. It stretches the graphene, and therefore it develops some band. Now, what is that graphene nanoribbon? GNR. Electrons in graphene are confined in the two-dimensional X and Y. Graphene is a two-dimensional material. In addition to the two-dimensional confinement, that means in graphene, electrons are forced to move in two dimensions. But in addition to this 2D confinement, graphene electrons can be further confined into one direction, supposing only X direction, by forming a narrow ribbons. Forming narrow ribbons. The width confinement results in a split of the original two-dimensional energy dispersion of graphene into a number of one-dimensional modes. So if we just cut the graphene into small nanoribbons, less than 50 nanometer, what happens? The original bands which were there, they develop several mini bands inside the main band. So there is a band gap between the mini bands, and that creates the band gap. These quasi-1D graphene ribbons of semiconductors with a finite energy gap called the graphene nanoribbons with width less than 15 nanometer. The properties of GNR are quite different from those of graphene. For example, carrier mobility decreases as the gap increases. Now this is the graphics of nanoribbons. One is called armchair and one is called zigzag. That means if you cut the graphene in such a way that one of the edge has this armchair-like appearance, then we call it armchair type, whereas another has this zigzag arrangement of the carbon atoms at the edges. That is what is called zigzag. For the properties are armchair, further properties, armchair graphene nanoribbon can be imagined as an unrolled carbon nanotube. That is, if carbon nanoribbon is cut and stretched, then it will become an armchair graphene nanoribbon. If a graphene nanoribbon runs in the armchair direction, that is, if the long edge of the ribbon shows an armchair pattern, then it is referred to as an armchair nanoribbon. Here you can see in more detail, this is the width direction, this is the length direction. And the armchair should be in the length direction, but in the width direction, it will be again zigzag. Similarly, you can see this is the length direction and this is the width direction. In the length direction, we have armchair-like structures. And another interesting feature of this is that there are two carbon atoms, I mean, inside the graphene, one carbon atom and the other carbon atom are, I mean, the nearer carbon atom is not facing the same. So therefore, we name them A-type carbon atom and B-type carbon. So in this armchair structure, you have AB carbon atoms along the length. Here also in the other edge, AB carbon atoms. Is the difference. And the other properties are armchair GNR are metallic or semiconducting. Armchair GNRs have energy gaps which decreases as the function of increasing ribbon width. The bond length of carbon atoms at the edges are shorter than that in the middle of the atom. So zigzag structures. Zigzag ribbons have the honeycomb network oriented in such a way that the edge is made up of triangular edges of the hexagon, as you can see. And zigzag GNR has a zigzag edge in the longitudinal direction, in contrast to the zigzag CNT, which has a zigzag pattern in the lateral direction. The armature and zigzag directions run perpendicular to each other in the graphene lattice. This has the confusing consequence that an unrolled zigzag nanotube is an armchair nanoribbon and an unrolled armor nanotube is zigzag ribbon. So that is the, and one very interesting important difference is that in zigzag all the A-type atoms are on one edge and all the B-type atoms are on the other edge. Whereas in AC, we have seen that they are AB at both the edges. Now, electronic properties. Calculations based on tight binding theory predict that zigzag nanoribbons are always metallic. Recall that armchair GNR can be either metallic or semiconducting depending on their width. The electronic conductance is favored for one spin direction, which may have implications for spintronics also. Another peculiarity of zigzag nanoribbons is that a perfectly conducting channel was predicted in tight binding models, even in the presence of long-range impurity scattering. Like the armchair GNR, the zigzag GNRs have the same hierarchy of band gap width relationship. We'll just see further about it. In addition to the self-developed band gap in GNRs, additional amount of band gap can also be introduced by other means. Like this is a graphic showing the induced energy gap in the armchair GNR. So there are two ways: applied strain or chemical adsorption. Chemical adsorption of other materials and also it will produce band gap. Now, induced energy gap with zigzag, we have four ways: apply electric field, then edge modification, chemical doping, and chemical absorption. So I'm not going to very detail of it. Band gap engineering in GNRs. Recall that the band gap of GNR depends on its width and crystallographic direction. Some simple, it does not depend on the crystallographic direction, as we see. Some simple calculation based on quantum mechanics will give an estimate of the band gap. It factors responsible are quantum confinement in one direction and graphene's linear dispersion at low energy. See here, quantum confinement in the x direction results in allowed wave functions like this, sin kxx, and where kx is equal to n pi by w. N is a number, that is the integer. N can be both positive and negative, and w is the ribbon width. So the dispersion is this, E is equal to h cross Vf a square. To obtain allowed energy levels, you get this, and the gap between E1 and E minus 1, which comes out to be 2h plus Vf pi by W. This is the band of graphene nanoribbon. If you take experimental data, then you can make a empirical relation or called scaling law, like the gap is equal to some constant alpha pi width minus some other width, having the constant width. Where alpha is 0.2 electron volt and W star is 16 nanometer. Then also this empirical relation also gives to some extent very accurate prediction of the band gap. And the result is that the band gap is inversely proportional to the width of the nanoribbon. The density functional theory calculates LUs of ranging from 0.3 to 1.5 electron volt, depending on crystallographic orientation and age termination. Now, energy gap versus crystallographic direction energy gaps as a function of relative crystallographic orientation of two devices called set D1 and D2 are shown. These two devices set have width similar W 40 nanometer, 25 nanometer, but different crystallographic directions, and the dashed lines show energy gap for each set as predicted by the average given width of that set. You can see that the thing is the average. So you observe that there are 7 energy gap that scales inversely with given width and has no dependence on crystallographic direction. This is width dependence again, what we have already studied. Some experimental studies by other group have been depicted here, and you can see this is the curve which shows that E gap is equal to alpha by W minus W star. And remarkably, energy gap as high as 200 electron volt, milli-electron volt is achieved by engineering GNR with down to 15 nanometer. Now, inverse energy gap versus width, this is a straight line, as you can see, because that is a curve, so it is 1 by W, so therefore 1 by E gap against W. Yeah, this is the theoretical graph of this energy band gap versus width, and it has been plotted from this 2h plus b by pi, the relation that we have already given. Now, these are some interesting results of GNR. Lee et al. Developed a chemical group to synthesize GNR of ultra-smooth edges and observed that all the sub 10 nanometer GNRs were semiconductors which facilitated the fabrication of GNRFET with an on to off ratio of 10 to the power 7 at room temperature. So, very exciting. Next, while GNR research started with a view to reduce bandwidth, researchers have also explored other possibilities, like Baringhaus et al. Prepared a 40 nanometer white GNR epitaxially grown on silicon carbide and observed a ballistic transport in excess of a distance of 10 micrometers. So this is interesting. This is interesting because ballistic transport of 10 nanometer is unthinkable in the present scenario of conventional semiconductors. Now, in addition, they observed an equivalent sheet resistance of their GNR below 1 ohm per square, which surpasses the theoretical prediction by more than an order of the The epitaxial GNR is thus expected to be significantly important in advanced nanoelectronics. Now, GNRFET, application and experimental studies, as well as theoretical models of graphene nanoribbon have been reported by several authors. You will see that the literature is zoomed with number of papers, but theoretical and experimental results have shown that GNRFET can potentially be good transistors with high ion to IF ratio and low subthreshold swing. We know subthreshold swing predicted for common semiconductor is 60 millivolt per decade, not below that, but GNRFET is much below that. We'll see. Basically, GNRFET is a transistor whose channel region has been replaced by semiconducting graphene nanoribbon. That is unchaired type nanoribbon for the channel region of the GNRFET. Modeling proceeds via the schematic structure presented in the next slide. So we have taken a scheme which is already there in, by Rizzi et al. In Journal of Applied Physics. So that is the scheme adopted, and the theory further, the rest of the theory also is developed on that same basis. So we have a highly doped substrate of silicon, which is serving as the back gate also, and then a thick layer of dielectric over the substrate. The dielectric width is WB, that is the thickness of this. Then the graphene nanoribbon, yellow line, it is put on the over the dielectric, then over the graphene another layer of dielectric, which is a width of WG. And this is the gate metal, source contact, and this is the drain contact. And there are two gates. One is called a top gate of smaller in length, and the back gate is it covers the entire length of the graphene nanoribbon. And sorry, the back gate is given a positive voltage in order to induce carriers in the graphene nanoribbon. So this is electrostatic doping process. So this electrostatic doping is used here to produce carriers inside the graphene nanoribbon, whereas the top gate is given a negative voltage which is used to control the flow of electrons in the n-type channel. So this top gate is to control, back gate is to doping, and the drain to source voltage, that is also positive. It allows current to flow through the GNR channel. The GNRFET under consideration is based on a structured GNR. Instead of single GNR, actually, which can support only a small amount of current, we can take an array of graphene nanoribbon and the graphene nanoribbon, and distance between them is very, very small. ES is the distance between two which is much less than D. D is the width of the graphene nanoribbon. So I have changed the symbol because of from. So the edges of the nanoribbon are connected to the conductive areas serving as the source and drain. Highly conductive substrate plays the role of the back gate, while the top gate is used to control source of substrate current. Then modeling approach, it proceeds via the dispersion relation, which is like this. Those who are not in theoretical motivated, let's keep this, no problem. And here this energy versus wave vector relation is given. V is the velocity in graphene, which is 10 to the power 6 meter per second. And so the high value, therefore, carriers in graphene flow like a relativistic particle. That is why we use that theory. So quantization corresponds to equation 1 of electron and hole energy spectra in nanoribbon due to electron and hole confinement in one of the lateral directions, causing band gap between lens and pulse. Channel section adjacent to the source and drain contacts are highly conductive, so that these are equipotential. The potentials are equal to the potential of the source and drain contact. That is, phi is equal to 0 at the source and phi is equal to 3d at the drain contact. So the equation to from the beginning, what we do is that we solve for the potential distribution or the surface potential on the graphene nanoribbon channel. In order to determine the surface potential, we use a Poisson's equation, modified Poisson's equation like that given at equation 2, where we have WB, width of the back, thickness of the back gate dielectric, WG, thickness of the top gate dielectric, and phi is the potential at any point, and this is the dielectric constant, and this sigma plus is the sheet carrier density of holes, and sigma minus is the sheet carrier density of electrons. And that means this is hole minus electron, so net charge with boundary conditions that I have already mentioned. Phi phi at minus LD by 2. LD is the length of the channel. So we are taking coordinate system at the middle of the channel. So left side source end is located at Lx is equal to minus LD by 2, and the drain end is located at x is equal to plus LD by 2. So the phi at this place is Q and PD, and these are the other parameters. Now, potential distribution, in order to solve for the potential distribution, electron and hole distribution function in the subband 1 in the source drain is given by this, where EF is the Fermi energy, delta is the band gap of the nanoribbon, and kVt is the thermal constant. The electron and hole gases are considered non-degenerate, where EF is the Fermi energy formed from the middle of the energy gap, and delta is the value of the energy. Now, the electric potential, electron densities, and the Fermi energies at the source and drain regions are related to each other by relation of this form. This is solution. Okay, please don't further go into detail. And this is solution for source and drain and carrier density. A1 is modified Bessel's function by considering the relationship between the electron density and the electric potential from equation 2. One can arrive at the following equations governing the potential distribution in the active region. This is the after simplifying, we get equation 6 and equation 7, and the potential distribution at low top gate voltage. When top gate voltage, the magnitude of the top gate voltage is small, very small, then the equation simplifies to equation 8, and when it is large, it simplifies to 9. So equation 8 and 9 can be solved by the two-phase boundary conditions, and we get equation 10. Equation 10 is the potential, where lambda is the given screening length, and this is the at V is equal to 0, as follows from equation 10. The function phi exhibits the minimum, and that minimum is given by this. Here, ED is much greater than kVt by E, and LD is much greater than lambda. The lambda is less than. The general value of the drain voltage variation is equal to this, which is very small due to the cos hyperbolic factor much greater than 1, and can be disregarded, so that ultimately we get this phi m is equal to simple relation like this, minimum. Now, potential distribution at high backgate voltage, quantity playing the role of the screening length is rather small. In this case, the length of the region near this LG by 2, in which the potential changes from phi equal to 0 to phi greater than kVt, and from phi equal to Vt to phi equal to phi minus Vt greater than kVt, is small in comparison to top gate length. In such short regions near the middle, the potential distribution can still be described by equation 10. However, in a significant part of the active region, the electron charge, which is in such a situation exponentially small, can be disregarded, and the last exponential term in 6 and 7 can be omitted. And after this simplification, we get equation 14, and I resulting from 45 given by 50. Now, and at Vt is equal to 0, minimum is executed by phi 60, and this phi m is given by question 70. So, actually, by big equations, nothing to convince, and they have been plotted and see the graphs, then we can be able to conceive something. figures in the next slide show the example of spatial distribution of electric potential along the channel, that is in the x direction in the active region of GNRFET, with the parameters specified here under the assumption that different values of the top gate voltage and drain voltage PD. As shown in the figure, in the next slide, the distribution of potential clearly sags, and the barrier height for electrons near the center increases with increasing absolute value of the target potential. Let's see the next. Yeah, this is the plot of the potential, that means phi against the channel coordinate. So you can see if gate voltage increases, negative gate voltage -7.5, -0.7, -0.8. This is 7. Then if the gate increases, this becomes 7.5. This becomes 8. That means as Vg increases, the potential sags more, or in other words, the potential barrier for the electron increases. Barrier for electron from source to travel this. So this from 0, if you drop it, and this is the barrier height. The barrier height will be gate. So the gate is actually what is doing. If negative gate values is increasing, then the barrier is increasing, therefore current will be less. Figures in the next slide depicts the spatial distribution of potential different drain voltage. Okay, this is at a different. Yeah, this is 5 versus coordinate at different drain voltage. In different drain voltages, you can see that the barrier height is not changed, but barrier height for electrons from the source side is not changed. But the barrier height for electrons from the drain side changes here. You can see it is equal to 0.1 volt, 0.3 volt, and 0.5 volt. So gradually increases. VD increases, then the barrier for electrons from drain side to enter the channel increases. This is your potential plotted in the channel region for different channel length. So this is for channel length 100 nanometer, this is for 200 nanometer, and this is for 300 nanometer. Okay, for 300 nanometer you can see is the original that we have seen. And for 200 nanometers, it stops here because this is 200. 200 is 100 and 100. 200, and this is 50 and 50. So it is 100 nanometers. So here also, as Lg increases, the potential barrier increases enormously. Calculation of current density. Considering the source drain current determined by the electrons, overcoming the potential barrier under top gate, the following formula can be used for calculation of current density. This is a standard formula, so nobody can refer to it to get this. So J is equal to this, where this P is given by this expression. Then after some simplification, you get expression 19, and then M is determined by the formula we have already seen, and at moderate and high voltage, equation 19 corresponds to average performance velocity. It is equal to this. You see that the speed of the thermal electron velocity actually is exponential factor in current density depends on the band gap. This is the now current versus drain voltage. Current versus drain voltage, you can just make some manipulation, and that this current is proportional to this. So this can be further analyzed like J is proportional to VD. If VD is much less than this, and J is constant if this is much less than VD. That means for low VD, this is a linear relation, and for high VD, high drain voltage, we get a saturation region that is constant. Similar to field effect transistors, we already know. So similarly, this is J proportional to this, is proportional to this, and the result is same. Result, these two figures represent the source. You can see is the result. Drain voltage versus current density for different values of the gate voltage. You can see initially for low VD, the current linearly increases, almost linear. But when VD exceeds 0.1 volt, then all the currents saturates, constant, it becomes constant. That means, and if VG is changed from -7 to -17, you can see the current drastically reduces. The saturation current drastically reduces. Then -0.75 further reduces drastically. So therefore, this saturation current is extremely sensitive to the change in the gate voltage. Therefore, the gate can be very suitably employed to control the current, and you can also keep a very good on to off ratio by this process, by the Nanoribbon GNRFET. Yeah, this is the another graphics of the same type, and drain voltage versus current density. And same VG, different VG, and the trend is same. Only difference is that here backgate potential is 2 volt, and here backgate potential is 3 volt. Now current versus gate voltage. We have already seen this expression already earlier. So for low gate voltage also we have one expression, and whereas for high gate voltage, and we can see that result for ID versus VG. This next two slides will show these graphs, ID versus VG at high absolute value of VG, and ID versus VG at low absolute value. The curve should show linear trend in both the figures and for both the values of the VG. The slopes are, however, different. High slope at higher VG and low slope at lower VG. This is the graph. This is the slope of the straight line actually, and the slope is high at higher absolute. This is lower absolute value of gate voltage, and this slope is relatively small. Result for channel length dependence. So channel length dependence, the next two slides will show current density is a function of drain and gate voltages respectively. In the first figure, the current density decreases with increasing gate length, while the second figure it shows exact opposite. That the current density increases with increasing gate length. In the second figure, all curves are intersecting at a point called inflection point. But you see here, you will see the if LD is increasing, current is decreasing. This means a saturation current, and but here LD is increasing, then current is increasing. That's the opposite trend of the other period. That means with respect to gate voltage, the current shows an opposite trend that with respect to the trend. Why? Because gate voltage is always negative, and whereas increasing gate voltage actually reduces the current. Therefore, this is the observation we are getting. Then result, yeah, results backgate dielectric thickness dependence. Backgate dielectric, that means WB. So there are two figures for that. Again, drain voltage versus the next two figures show that the current density is strongly influenced by thickness of the back voltage. So the current density has least, let's see, similar trend is here. Also, therefore the current very sensitive to small WB. Let's see here WB increases, then the saturation current decreases and drastically at about 140 nanometer it almost becomes zero. WB increases, current decreases. Here also WB increases, current decreases. Same trend. Top gate dielectric thickness dependence, that means WG dependence. You can see here WG 10, 50, 20. So just the opposite. As WG increases, current increases. Here also same thing. WG increases, current increases. WG increases, current increases in the gate voltage also. Temperature dependence. Next two, three figures we see how temperature changes.
Excuse me, Prof. Excuse me, Prof. You have 5 more minutes left because we already reached 45 minutes of presentation.
And I have to finish by next 5
In
minutes.
5 minutes. In 5 minutes, is it okay? How many more slides do you have?
How much time you will give me next?
Okay. Thank you.
How much time you allow me next?
Another 5 minutes?
Another 10 minutes. Okay, thank you so much. The next three figures show that current density is strongly influenced by the temperature. Interestingly, the current density increases with increasing temperature in the ID versus VD curves, while it shows the opposite trend in ID versus VD curves. Here the current density decreases with increasing temperature. Third figure shows channel length dependence of current at different temperatures. Lower LG gives higher current, but lower E gives lower current. Let's see. There are things here. Temperature increases from 100 to 300 K, then the current increases from almost zero to a very high value, saturation current. And this is the other graph. As temperature increases, here the current decreases. Just the opposite. And here this is the length dependence. Current increases, but if temperature increases, then current increases. Temperature increases, current increases. Channel length decreases, current increases. These are the dependence. And then quantum capacitance is a parameter very much used in the modeling of nanoscale devices. Therefore, it will be incomplete if we do not model the quantum capacitance for the graphene nanoribbon. So I give some hints of that. General expression for quantum capacitance is any capacitance is dq by dv, but suitably you have to take charge and the potential. It is a two-dimensional materials like graphene or graphene nanoribbon. it arises. And it is slightly different from the classical capacitance because in two-dimensional materials, the charge is continuously distributed from top plate to bottom plate. But whereas in classical capacitors, the charges reside only on the plates, top plates and bottom plates, and in between there is no charge. So that makes the difference of quantum capacity. But dq is the charge in the channel. If dn is the sheet electron density, then dq is equal to E into dA. dV is equal to energy by A. So then if you combine these two, you get quantum capacitance equal to Q square into dN by dt. That means the rate of electron density with respect to energy. So you can see this is the standard equation for calculating carrier density in a semiconductor, that is density of state dE, Fermi distribution function Fe, and small q. So this dE is equal to, this is the relation for a graphene nanoribbon, the density of state gives this relation, and the Fermi function gives this relation, and quantum capacitance expression can then be that we can simplify this equal to this, and then gate capacitance is the parallel of insulator capacitance and quantum capacitance. C in and CQ, no, not parallel, actually it is series, where C in is given by classical capacitance relation, transconductance is defined as this, conductance is defined as this, these are the standard relations, and cutoff frequency is defined as this. Then quantum capacitance for the insulator it is standard, and for quantum and gate capacitance, so the same trend. Figure in the next slide, we see. Can say up to point -0.2 volt gate voltage, the total capacitance is almost zero. This is the total capacity, quantum capacity, green line, and insulator capacitance is the blue line, and this is gate capacitance or total capacitance, the red line. From -0.22 or 0, almost increases to half, and after 0, it just suddenly, and at about 0.2 volt, it becomes saturated. Conductors and transconductors variations are like this. This is the up to 0.65, which is almost 0 transconductance, and thereafter it steeply rises. Conductance is just opposite, up to 0.1 volt, it is very high from 0 to, and after 0.1 volt, it reduces to almost 0. Cutoff frequency, you can see this is a normal plot of cutoff frequency. We get a peak at 0.65, and then it increases. If you take a semi-log plot of the cutoff frequency, you get a completely peak here. Peak. Then band gap dependence of current. This is a standard relation. If you energy band gap is changed, the energy band gap can be changed only by changing the width of the graphene nanoribbon. And if width of the graphene nanoribbon is varied, then correspondingly energy band gap can be determined. And as a function of energy band gap, the current is, that is, the energy band gap decreases, then the current increases. So this is standard relation. I think I have come to the end of my talk. So I give you the summary. Analytical formulae for potential distribution and current density in GNRFET have been derived following some published work. We have then implemented a MATLAB-based model for the GNRFET. The GNRFET current voltage characteristics, that is the dependencies of the source drain current versus the drain voltage, as well as the backgate and topgate voltages, were calculated for devices with different geometric parameters such as thickness of the gate layer and top gate length by using this model, and the following results are presented. So what result we have presented? Effect of top gate voltage, drain voltage, and top gate length on the potential distribution. Effect of top gate and back gate thickness on the current density versus drain voltage. The effect of top gate and back gate thickness on the current density versus gate voltage. The effect of energy band gap on the device current density. The effect of temperature on ID with respect to dependence on VD, PG, and LD. Quantum and gate capacitance is a function of gate voltage, and conductance as a function of VD, and transconductance and cutoff frequency as functions of gate voltage. These are the things. A complete summary. And this work is in progress, so further it can be done. Now, any questions?
Okay, thank you. Yeah, thank you, Prof. Dash. Okay, so now I think I will look into the chat box now. There are two questions here by Mr. Muhammad Fauzi bin Fakir Muhammad. Dear Prof, is there any working graphene transistor which could be implemented in a circuit like low noise amplifier circuit? That's question number one. Question number two, in GNRFET, did the formation between armchair and zigzag affected the output of the transistor?
I think, can you please give me in the writing form?
Yeah, if you look at the chat box now, Prof, can you go to the chat box now?
Chat box.
Yeah, chat box.
Should I?
If you look down there is like a chat. Can you find chat box?
Okay, I have got it.
Okay, good. So there's two questions there.
I'm unable to get it clearly. Not getting. Please just repeat for my sake.
I'm sorry, Prof?
I'm not getting in the chat. Unable to find out the. This is chat in chat box, no?
Yeah, maybe if you, there's a chat box. You go to can you go if you look, you move your cursor down there. It is and then there are a few circles come out, and then you can just click on the chat. There is like another circle inside there. It's like a circle bubble. The chat bubble. You click
Chat
there.
participants. Chat
participant, not participant. The other one next to participants. Chat box. Click that, and then and then you go to the most down, the lowest. You scroll down, and then you will see the question for you. The Prof.
Okay, thank you. In GNRFET, did the formation between armchair and zigzag?
No, I think not that one. The question starts from Muhammad Fauzi. The last two questions.
So question is, in GNRFET, did the formation between armchair and zigzag affected the output of the transistor? Of course, certainly, but you cannot also use zigzag because zigzag is totally metallic, so it cannot be used in the transistor. Only armchair is semiconducting, therefore that can be used. Next question is just second question. So first I answered the second question. Okay.
Is there any working graphene transistor which could be implemented in a circuit like low noise amplifier?
Is there any working graphene transistor which could be implemented in a circuit like low noise amplifier? Yeah, definitely. Working graphene transistors are now rampant, and it has come to the market. I mean, commercial market also. and a very showing very good result.
Is there any question from the participant? Any other participant? Okay, if there is no question from the participant, so I would like to thank you, Prof. Dash. I hope all doubts on the topic have been cleared. Okay, ladies and gentlemen, may I thank you very much for the participant. Okay, before that, I would like to invite our chair, Professor Dr. Nur Hayati, to give her remarks. Prof. I would like to invite Professor Dr. Nur Hayati, the chair of IEEE EDS Malaysia section, to give her appreciations remark.
Okay, Assalamualaikum. Can you hear me?
Yes, Prof.
Okay, Assalamualaikum and good afternoon. Okay, on behalf of EDS Malaysia, I would like to thank Prof Zhou and Prof Dash for the excellent and interesting talk on the novel integrated circuits and graphene nanoribbon FET. So I would also thanks again for supporting EDS Malaysia to make the DL session so rewarding. And as a token of our appreciation, ED Malaysia would like to present Prof Zhou and Prof Dash a virtual certificate. Okay, and I would also like to take this opportunity to thank all the ED Malaysia ExComs and all participants for making this session successful. Okay, thank you.
Dr. Mai, can you present?
Yeah, we are waiting for the virtual certificate.
Yes, hold on, hold on.
Well, I'm also thankful to all of you participants and also the office bearer of IEEE Malaysia chapter for inviting me to this actually real
Thank you, Prof.
lecture.
Dash.
And I would definitely wish in the future to have a non-virtual, actually face-to-face MQ or DL, and it will be very interesting for me. Okay.
Okay, thank you, Prof. Dash. Okay, thank you, Prof. Dash. So I hope this is our first time to deliver certificates virtually. So thank you very much for the support from the distinguished lecturers.
Okay.
Thank you, Dr. Zhou.
Yeah. So I disconnect from the meeting.
Okay. Yeah, thank you
We're
all.
having photo session right now.
Okay, thank you, Prof. Dr. Hayati, for presenting the certificate of appreciations virtually. So now I think we would like to have a photo session for this event. So, Dr. Hasina, how are we going to do this? So we hope that everyone's to turn on their camera, I believe. Can you all turn on your camera? Okay. Okay. I can see not all turn on the camera yet. Okay. Taslina, or Dr. Mike, can you please like print screen? How are you going to do this? I have no experience in
I'm
this.
going to, Dr. Zhou, I'm going to take picture. I'm going to take picture. I'll snap the picture.
Right. Okay, thank you.
Smile, everyone. Smile.
Our Prof. Zhou is not turning on the camera.
Oh, some are driving. Muhammad, you're driving.
Huh?
Some are driving.
Mama driving, Mama.
Okay, I need to go from screen to screen because you have many participants today. Donna, it's a bit slow.
Smile, smile. So serious face.
Okay.
Okay, thank you. Then okay. So thank you all. Thank you very much for your participations in this virtual IEEE distinguished lecture sessions. I hope you enjoy and learn as much knowledge as possible. So before we end this session, I hope you can click on the feedback form. Okay, I'm going to write down now. Okay, this is the link. If you look at the chat box now, this is the link to the feedback form. Okay, after you fill in, then we know that you are, you have completed attending this session. So we will email you the e-certifications of participations in this lecture session. Okay, all right. To speakers and NESCOM, please stay after we end this program, as we will take another picture with the EXCOMs. So again, I thank you all for your participations, and I hope all of you can participate in our future activities in IEEE EDS Malaysia. The next activity will be starting tomorrow, which is our IEEE International Conference on Semiconductor Electronics, ICSE 2020, from 28 to 29 July 2020. This is going to be our first virtual conference as well. So here we have come to the end of this program. So I hope you will fill in the feedback. Okay, so now we will end this program. I thank you and see you again soon. Wabillahi taufiq. Wassalamualaikum warahmatullahi taala wabarakatuh.
Thank you. Bye-bye.
Prof. Xing, hold on, Prof. Zhou, hold on. Hold on.
Prof. And Prof. Dash, please
Dash,
stay.
hold on.
Yeah.
Semua community dah ada ke? All EXCOM. Oh, well, available. Okay, Zhou, how many of us?
How to, Dr. Zhou, how to how to do it?
Kejap sebab because sometimes some of them they don't realize they just keep on the PC. I think let me just Google kejap. How to this. Okay, how do I? You have to go to in the meeting window, open the participant, you select the attendee, okay, and then you choose expel. Dr. Mai.
Expel, huh? Right.
You know.
Okay. There are quite a
Macam
number of people.
Yeah.
I have to go one by one.
Okay, there you go. Okay, that's finish. You can just let us know.
Sure. Okay, so can someone double confirm whether these names are all I didn't miss out anyone, yeah? Okay, done, Dr. Zhou.
Dr. Nafa, can you please turn on your camera? Dr. Nafa. Dr. Nafa. Okay lah. Dr. Has.
Yes.
Yeah.
Dr. Has.
Anybody else? Dr.
Can
Has, UPM?
dah naik kereta dah. Dr. Has, turn on je. Dr. Has. Dr. Nafa. Okay. Keep. Dr. Nafa. Alamak, tak nak tidur lah. Dr. Nafa must be somewhere. Maybe you can take picture now. Dr. Mai. At least lah. Okay, with the... Where's Dr. Prof Dash? He left already.
He left.
I think Prof Dash has left. At least we have Prof Zhou. Thank you, Prof Zhou, for staying.
You're welcome.
Yeah, thank you, Prof.
Our
Zhou.
Malaysia chapter has been very active.
Okay, thank you.
Yeah.
I've been to Penang chapter, but not the KL.
Okay, so maybe next year we can invite you face to face,
Yeah.
Prof. Zhou.
Yeah.
Been to KL, but not your chapter. Your university is within KL region?
Yeah, most of our universities around KL, yeah. Except Dr. Nurul Izzailah, she is near your place in Johor.
Johor.
Yeah.
Very close to Singapore.
Well, because of the coronavirus, even so close, we cannot travel.
Right, yeah. Okay, so
Okay, done.
okay, thank you so much, everyone. Thank you, Prof. Zhou.
Thank you, everyone. Yeah,
See
Thank you,
you then.
Prof. Congrats, EDS.
very good experience.
Thank you, Prof.
Yeah.
I suppose I don't need to feedback anything to EDS, right? You are going to do the report.
Dr. Susi?
Dr. Susi?
Yes, I
Yeah.
think after this we fill up the feedback form, DL feedback form. Prof.
So I don't need to do anything, right?
No, it's just Prof. Nohayati need to
Yeah.
fill up the DL feedback form.
Okay.
Thank you, Prof. Zhou.
Thank you. Thank you.
Thank you, Prof.
Bye.
Prof.
Bye. Mhm.
Bye.
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 Thank you.
Good job. We did it.
Alhamdulillah.
Alhamdulillah.
First phase. Debaran first. Okay, thank you, Dr. Suzy, Dr. Zhou, Dr. Mai, Dr. Has. Okay, yang tulang-tulang belakang ni.
Thank you.
Yang penting yang tulang belakang. Dr. Thank you. So Alhamdulillah we have done for the first phase ya. So simpan tenaga untuk debaran tomorrow and the following day.
Webex quite okay. Webex is okay. I think the time limitation lah is so the keynote, the chair, the session chair have to control the time.
Yes.
Tadi rasanya saya punya network masa Prof Dash tu dia ada ni lah, ada ni sikit
Saya pun tak
ada kurang jelas lah, tapi Prof Zhou pun tadi very clear lah.
Okay, for tomorrow, how are we going to tell about 5 minutes more, 10 minutes more? Ada cadangan tak? Macam mana nak bagi tahu 5 minutes more, 10 minutes more, macam mana?
Saya masih conventional, saya tanya Bell.
Zala, any suggestion? Boleh tak macam host share screen?
flash screen boleh kot masuk share screen.
Ada bling-bling tak?
Tapi bukan dia kena unshare dulu ke? Tak.
Macam tadi boleh je kan? Host boleh share je kan? 5 minutes more, 3 kan? Tak boleh?
Maybe the host can
slide yang kita bagi 5 minutes.
I think the host can control.
Have to masuk and tell lah. Macam satu
jadi macam ni lah, physical.
Hello? Hello?
Zaila, tomorrow ada sekretariat yang akan jadi host ke?
I think
untuk control session.
hello?
Yeah, we can hear you, Dr. Zaila.
Boleh dengar tak?
Boleh. Go on, go ahead.
We can hear you.
Okay.
Dengar tak? I think we can I think we can as a host we can share the screen by like 5 minutes to go, but then the presenter has to reshare again their slide, so maybe so it will be like while presenting their presentation, so as a host we can share 5 minutes, let's like 5 minutes left. But then we have to tell the presenter to share again the slide. So it would take like
betul lah, dia ada gangguan lah kan?
Maybe as a chair session we can just interrupt while the presenter presenting, we can just interrupt a few seconds, say that we left 5 minutes, something like that. Okay.
So there is no high tech punya cara lah ya. So kena guna still conventional punya.
Ke boleh introduce Bell ke apa kot? Bell.
Itu saya tanya Bell je, saya ingat dekat hotel
macam
kan.
Prof cakap tu good idea juga. Masa awal session chair cakap bell sound ke tapi kena figure out lah bell sound daripada phone ke.
Daripada phone.
What do you think, Prof Zahirul? Tomorrow how are we going to control the time?
Prof Zahirul. The IT expert here.
How to add on the physical bell.
You're on mute, Prof Zahirul, you're on mute. You're on mute.
Let me unmute. I have the control.
Okay.
You have the control.
I think a chair can mention 5 minutes more or PIC. Each session has a PIC. He can just mention during presentation you have 5 minutes.
Just interrupt, right?
Yes.
Interrupt. Okay.
I think that is more.
Unless Dr. Mai can create new
The sound.
Alternative, right?
Actually, I will also remind the PIC to take note on the time in case the chair doesn't realize the time. So the host, the PIC will take charge too. But the instruction to chair already highlight that chair has to check the timing.
Yeah.
But then the PIC also will do the checking too lah, insyaAllah. Okay.
The problem is even in normal conference, the time will run.
Yeah.
Then we have to show the placard, right? Minutes, 10 minutes.
Correct.
Yeah.
But here it's like macam tak proper lah. It's like tiba-tiba interrupt macam tu. Tapi we have to lah.
Or there is in the during presentation there is annotation. They can write 5 minutes. The IC can write using the annotation.
Maybe we can write on the chat box too, but maybe the presenter didn't realize the chat box.
On the slide, not in the.
Can we add on the slide?
On the slide, using the annotation, there is a marker, then we can write 5 minutes. Now also after that, need to erase. It will appear during the presentation.
Like lecture, okay.
Yeah.
Oh, okay.
That erase.
I'm afraid PIC shaky, right?
I'm not sure.
They will erase everything.
Or pointer. There is a pointer just to
do that, Prof. Teach us.
no. Okay, for example, let me share some slide. Let me.
Yeah.
We have a training for WebEx. But I think WebEx
is it only for the presenter while they're presenting the slide, then only we can do the notation? Or
Yes,
as a host also we can do the notation while the presenter presenting the slide?
Yes.
Okay.
Of course, you can try.
Okay.
Let
What
me.
about pass host, Dr.
You're the host.
Pass to Dr. Suti while Prof presenting, try do the annotation.
Someone has to.
I think Prof. Niza is fine. I'm just afraid of
who?
The keynote speakers, the other two. Prof. Niza, I think should be okay.
It's okay, Prof. G. Prof. G. I will also remind him many times before the talk. Don't worry. I got the WhatsApp. I can text him. Just to remind first, So can we explore the annotation or whatsoever?
Okay, let me find because I am using another. For example, I share.
Okay.
And there is annotation top, or you can see annotation.
Okay, yeah. But anyone can write, is it?
Right.
But otherwise, anyone they need
You have to request to edit.
We have to request.
But for the host, I'm not sure whether he can write on this.
How about Dr. Mai try? Right click, add notation.
No, but
Dr. Mai, right click.
Then no, because I see the annotation request from Dr. Maizatul.
You need to approve.
Approve, yes. But
so we have to request to the presenter.
Yeah.
I see.
When they see interruption.
No.
It must be a permission, right?
I'm afraid the presenter become nervous when see the presentation. What was
writing that? 5 more minutes.
I think the presenter will read 5 more minutes.
What are you writing there?
No, or
they will read that.
instead of you can write five more minutes. So instead of take minutes.
Oh, okay, you can type.
Oh, okay, I can also type. Ah,
Yeah.
okay.
Because that's too small.
No,
It can
yeah.
be bigger.
Enlarge the font, Mai. Boleh tak enlarge?
That is not me typing, that is Prof typing.
Okay.
Oh, really? Sorry,
Sorry,
Prof. Can we enlarge the font?
You cannot enlarge.
Oh, really?
Yeah.
So I think that better, right? Just
Yeah.
jot down something 5 more minutes, something different from the written, right?
And after that,
You change to text, Prof. How do you change it to text?
no, there is in my annotation there is also T. T is there.
Okay, okay.
Okay.
No.
Right.
Okay, now you should. Okay.
Okay, okay.
I can type.
I'm not sure whether this is appropriate or not.
But I think, Prof, if you do annotation, the annotation stays. It will not go away.
No, then no, need to erase again. There is a button.
Yes, we can erase. Yes, we can
erase it. Okay.
Erase, yes. Oh, you know what erasing?
If we don't erase it, if we don't erase
Prof, how
it,
about
Stay
Prof,
there. It will stay there, Prof. It will stay there.
How
for the
about
next
if the Prof Zahiro, how
next
about
slide.
the next slide? Then the notation will still be there? No.
So,
Be there. I've experienced it when I present, someone annotate, and until I finish my slide, the annotation is there.
yeah, but it is.
They did not erase that, Dr.
Change the
Susi.
slide, Dr. Susi.
Yeah?
Even if you change to next slide, the annotation still there?
Oh no, missing already, gone.
Erase already, right?
No more.
But I need to close the annotation, otherwise my slide is not moving.
Ah.
Causing more trouble, so it is better not to use this way.
Yeah.
I think I'm sorry, presenter, you have 5 minutes left.
Yeah,
I think
better.
like that, very soft.
Be polite.
The
Dr.
presenter
Izaila,
will present.
politely. Don't worry.
Okay, okay.
Or else the presenter will get panic and then you cannot.
If I were the presenter, I will also get panic.
I think it's not only the presenter,
Yeah. If you use annotation unless close, then you are in this struggle.
Yeah.
It is not moving.
Yeah, at this moment we can just stick to the conventional method, right, Prof?
Yes.
Yeah.
At this moment, just in case if tonight Dr. Izaila can dream something new, right? But make sure the simple one.
Let's use the simple one.
Or any bell sound or something like that.
Yeah, okay.
Tomorrow, the photo session will also be done by the host, right? For each session? Dr. Izaila?
Yes, what?
The photo session, it will be similar.
Yes, by PIC, stand in charge. Okay.
Okay, for the parallel session, right?
Only one session, no parallel.
I think if you ask the session, then
Sorry, Prof.
which button?
I got carried away with the parallel session face to face,
Yes.
Continuous session, no parallel session.
Yeah, sorry, because this is the first time we don't have the parallel session, right?
Yes, correct. Yes.
And virtual.
Good job, everyone. Very good.
Okay.
Okay.
Thank you, everyone.
So I
Thank you.
hope, please take care of your health, okay? Good energy tomorrow. Don't be so stressful. Ketua Secretariat Leader, please don't be so stressful. Share everything with us. Okay, share everything with us.
Everything will be fine.
Yeah,
Okay.
share everything with us. Stressful alone, okay? So share with us. Right?
Okay, sure. Thank you very much.
Congratulations for today. Okay,
All right,
bye.
thank you. Okay, bye. All right.
Everyone.
Okay.
more thing.
One more.
No, one more thing. So I'm not sure. So whether we allow the other authors without any charge or not, but probably no one registered through the because
Yep.
What's that, Prof?
participant. So other author, we allow other authors whether without any charge.
Oh, we only allow for paid participant, right, Prof?
Yes, okay. How many paid participant? Already paid or not paid?
Oh, I mean a participant only, none until now.
Then in that case, can we allow other authors to attend if they are interested without any charge or no?
Hey, we have the walk-in class, right? That is, we already published, right?
Yes, we already published, but no one emailed me because I supposed to receive email of their receipt, but no one emailed me. So I believe until now, no one has pay for the walk-in.
Yeah, it's okay. After this, we try to remind because I got some networkings, right? So I would like to remind them. So we wait for maybe evening, right?
Somebody need to control the attendance, right? Because if anyone can access the link, then they can just join, right?
Yes.
How can we control?
Then we have to check.
ID.
Just join.
This link only circulated to the presenter only.
Yep.
I think.
Get the link only. I'm not sure if they presenter shared to their author or not.
But okay, how the host can control or
then host can just remove their.
can expel.
Host can expel. Host can expel.
Can ada there must be one policeman, right? Policewoman.
They enter, you expel. They enter, you expel.
And then they need to have the list, the name list.
Once in a while, I will enter to the room, to the virtual room, and check out the participant.
Okay,
if
please.
this is not the participant, I will expel.
To have a master list then. Or
So share master list lah,
But
right?
EDTM they control by email. Only the valid email can enter. If your email is not valid, you cannot enter.
Okay. So can we do that, Dr. Suzy?
I don't think, right?
I think this one already provided
Hi,
by
Dr. Sabirin.
Cannot, I think.
Tak boleh. So it's okay. We do it manually lah, right?
We did.
Tomorrow game of expel.
Expel.
I need to assign a new post policeman.
Expel officer.
Expenditure.
Expel officer. Boleh jadi expel officer. Nak masuk. Dr. Sabirin nak masuk. You can in charge as an expel officer.
Dr. Sabirin, you are
Expel officer. Must be a man.
Jom ambil nama dengan Dr. Sabirin.
Ada tau dengar tadi DL. Tapi lepas pukul 12 pergi ambil anak.
Tak suruh jiran. Kena suruh jiran.
Vice Chair, jom dengan Vice Chair. Tak berkenan boleh expel.
Somebody's in. So as a policeman, we have to expel.
It's okay. Nanti whoever we expel it virtually, we can invite to register EDS as a member. They love EDF very much, so please register as a member. Okay, Dr. Sabirin.
Smile.
Oh, my battery dah low dah ni, so I have to leave any minutes.
Me too.
Okay, me too.
I also have to leave soon.
Okay, alright.
Okay.
Dr. Sabirin.
Best of luck. Please share siapa ada problem. Please share the problem. Or share whatsoever lah. Okay, bye. Good.
Alright,
thank you. Okay, bye.
Bye. Thank you all. Thank you very much.
Good job. 4 days only.
Thank you.
Yeah.
Okay, bye.
Bye, bye, bye.
Bye.
Waalaikumsalam.
Thank you.